Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be continuing our lecture on acids and bases, and we've made it to the second objective. Here we're going to cover properties of acids and bases. Now, acids and bases are usually characterized according to their relative tendencies to either donate or accept hydrogen ions. Furthermore, aqueous acid and base solutions can be characterized according to their concentrations of hydrogen and hydroxide ions. So with that, the first topic of conversation here is the auto-ionization of water and hydrogen ion equilibria. Now, the auto-ionization of water, also known as the self-ionization of water, is a process where water molecules react with each other to form hydronium and hydroxide ions. Now, this reaction is really important in understanding the acidic and basic properties of aqueous solutions. Now, in this reaction, one water molecule donates a hydrogen, a proton, to another water molecule, forming hydronium ions and hydroxide ions. This reaction is reversible, meaning that hydronium and hydroxide ions can recombine to form water. Now, for this reaction, we can write the equilibrium constant. This is also called the water dissociation constant, Kw. This is given by the following equation, where we see the concentration of hydronium ions multiplied by the concentration of hydroxide ions. Please remember, for equilibrium constant expressions, we have the concentration of the products raised to their stoichiometric coefficients over the concentration of the reactants raised to their stoichiometric coefficients. We do not include solids or liquids in this expression, hence why water is not included in Kw. Now, at 25 degrees Celsius, Kw is equal to 1 times 10 to the minus 14. This value indicates that in pure water, the concentration of hydronium and hydroxide ions are both 1 times 10 to the minus 7 molar. Now, just as another reminder, Kw is an equilibrium constant. So unless the temperature of the water is changed, the value of Kw cannot be changed. So the product of the concentrations of the hydrogen ions and the hydroxide ions in an aqueous solution at 25 degrees Celsius, aka 298 Kelvin, must always equal 10 to the minus 14. However, of course, at different temperatures, then the value of Kw changes. Now let's further explore hydrogen ion equilibria. This refers to the balance between hydrogen ions and hydroxide ions in aqueous solutions. Now, the concentration of these ions determines the pH and the pOH of the solution. A p-scale is defined as the negative log of the number of items. So let us elaborate on that. Let's discuss acidic solutions. When an acid is added to water, it's going to increase the concentration of hydronium ions. It is going to increase the concentration of hydrogen ions. So for instance, if we added hydrochloric acid, this is going to dissociate into hydrogen ions and chloride ions. The increase in hydrogen ions is going to lead to a decrease in pH. So for acidic solutions, you're going to have a pH that is less than 7. What about for basic solutions? When a base is added to water, it's going to increase the concentration of hydroxide ions. So for example, if we were to add sodium hydroxide into water, it's going to dissociate into sodium cations and hydroxide anions. The increase in hydroxide ions is going to result in a decrease in hydrogen ions, and that is going to lead to a higher pH. So in basic solution, the pH is greater than 7. Now, the pH of the solution is calculated using the concentration of hydrogen ions. So the pH is going to be equal to the negative logarithm of the concentration of hydrogen ions. You can alternatively write the same expression in a different way as the log of 1 over the concentration of hydrogen ions. What about the pOH? The pOH is calculated using the concentration of hydroxide ions. So pOH is equal to the negative log of the hydroxide concentration. Now, the relationship between pH and pOH is that the sum of pH and pOH is equal to 14. This is really important to remember. Now, a direct consequence of this is that when pH increases, pOH decreases by the same amount. Now, let us summarize a couple of points here. For an aqueous solution at 298 Kelvin, a pH less than 7 or a pOH greater than 7 means that you have a relative excess of hydrogen ions and the solution is acidic. Now, for a pH that is greater than 7 or a pOH that is less than 7, then this indicates a relative excess of hydroxide ions and the solution is basic. A pH or a pOH that is equal to 7 indicates equal concentrations of hydrogen and hydroxide ions, and this results in a neutral solution. Now, something that students find difficult to do on the MCAT is carrying out calculations and conversions with pH, pOH, pKa, and pKb. So let's cover a couple of tips and tricks to help us do calculations without a calculator. We're going to start off with something that is easy. When the original value is a power of 10, then the operation is straightforward. All you have to do is change the sign on the exponent, and that will give you the corresponding p-scale value directly. So if you know that your hydrogen ion concentration is equal to 10 to the minus 3, the pH is just going to be a change in sign in the exponent. So the pH is going to be equal to 3. Now, if you know the pH, you can actually also calculate the pOH. This is because we know that pH plus pOH is equal to 14. So we can rewrite this to solve for pOH. That will be equal to 14 minus the pH. So here, if we know pH is equal to 3, then pOH is just 14 minus 3, which is equal to 11. Now you can do the same thing for Ka and Kb values. If you know that your Kb value is equal to 1 times 10 to the minus 12, your pKb value is just going to be a change in sign of the exponent. So pKb is going to be equal to 12. Now, more difficulty arises when the value is not an exact power of 10. Here, we can actually obtain a relatively close approximation of a p-scale value using a shortcut. This is the shortcut. You want to take your non-logarithmic value and you want to write it in proper scientific notation. It needs to be in the form of n times 10 to the minus m. Here, n has to be a number between 1 and 10. Then, by taking the negative log of this, we can simplify this calculation to minus log of n minus log of 10 to the minus m power. Now, further, we can simplify this writing to m is equal to minus log of n. Now, here's where it becomes really fun. Because n is a number between 1 and 10, its logarithm will be a decimal between 0 and 1. This is because log of 1 is equal to 0 and log of 10 is equal to 1. Now, the closer the n value is to 1, the closer the log of n will be to 0. And the closer the n is to 10, the closer the log of n will be to 1. And so as a reasonable approximation, we can write that the p-value is approximately m minus 0.n, where 0.n represents sliding the decimal point of n one position to the left, essentially dividing n by 10. So these kinds of rules are going to make your calculations a lot easier. With that being said, let's move on to the next topic where we discuss strong acids and strong bases. Strong acids and bases are substances that completely dissociate into their ions in aqueous solutions. This complete ionization makes them highly effective in altering the pH of solutions. Strong acids, they're characterized by their ability to completely dissociate in water, releasing a high concentration of hydrogen ions. This complete dissociation is what makes them strong acids. Strong bases, on the other hand, are compounds that completely dissociate in water to release hydroxide ions, and it is this complete dissociation that makes them strong bases. Now here what you see is a list of the common strong acids and bases that you may encounter in the MCAT. I highly recommend remembering the strong acids and the strong bases. So the strong acids include hydrochloric acid, hydrobromic acid, hydroiodic acid, sulfuric acid, nitric acid, perchloric acid, and chloric acid. For the strong bases, this includes lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, and calcium hydroxide, strontium hydroxide, and finally barium hydroxide. These are our strong acids and bases. What about weak acids and bases? Weak acids and bases are substances that only partially dissociate in aqueous solution. So unlike strong acids and bases, which completely ionize in water, weak acids and bases reach an equilibrium state where both the ionized and unionized forms exist in solution. Let's start by talking about weak acids. A weak acid partially dissociates in water to produce hydrogen ions and its conjugate base. The degree of dissociation here is quantified by the acid dissociation constant Ka. Now, the general dissociation of a weak acid in water is represented by this equation right here. Looking at this, we can write the Ka value, keeping in mind that for equilibrium constants, we have the concentration of the products raised to their stoichiometric coefficients over the concentration of the reactants raised to their stoichiometric coefficients, and we exclude liquids and solids. And so the acid dissociation constant for a weak acid is equal to the hydrogen ion concentration multiplied by the conjugate base over the acid itself, the weak acid itself. Notice water is not included because it's a liquid and we exclude liquids from equilibrium constant expressions. Now, something to keep in mind is that the smaller the Ka, the weaker the acid and the less it will dissociate. Okay, now an example of a weak acid is acetic acid. This is a common weak acid. Okay, what about weak bases? A weak base also partially dissociates in water and it produces hydroxide ions and its conjugate acid. Now, the degree of dissociation is quantified here by the base dissociation constant Kb. Again, remember, for equilibrium constant expressions, we have the concentration of the products raised to their stoichiometric coefficients over the concentration of the reactants raised to their stoichiometric coefficients, and we exclude solids and liquids. So for a weak base, the base dissociation constant is equal to the concentration of the conjugate acid multiplied by the concentration of the hydroxide ions all over our weak base. Now, for this, the smaller the Kb the value, The smaller the Kb value, the weaker the base, and the less it will dissociate. So as with acids, water is not included in the equilibrium expression because it is a liquid. Now, an example of a weak base is ammonia. Generally speaking, we can characterize a species as a weak acid if its Ka is less than 1, and as a weak base if its Kb is less than 1. Now that we have a solid understanding of weak acids and bases, including their partial dissociation and their equilibrium constants Ka and Kb, we can naturally transition into the concept of conjugate acid-base pairs. This concept is closely linked to the behavior of weak acids and bases in aqueous solution. Now, when an acid donates a proton, it forms its conjugate base. On the other hand, when a base accepts a proton, it forms its conjugate acid. This proton transfer process, it highlights the dynamic equilibrium between acids and bases. So conjugate acid-base pairs, they consist of two species that transform into each other by the gain or loss of a proton. Now, some simple general principles to keep in mind are the formation of a conjugate pair. All right, every acid has a conjugate base that's formed by the loss of a proton, and every base has a conjugate acid that's formed by the gain of a proton. You should also know the strength relationship. The strength of an acid is inversely related to the strength of its conjugate base. A strong acid which dissociates completely has a weak conjugate base. Similarly, a strong base has a weak conjugate acid. The final point in relationship to this is the equilibrium considerations. In an equilibrium mixture, the position of the equilibrium, it can be influenced by the relative strengths of the acids and bases involved. For weak acids and bases, both the acid and its conjugate base are present in significant amounts. Now, there's another important concept we want to discuss here. When you have a weak acid dissociating in water and its conjugate base acting as a base in water, the combined reactions essentially represent the autoionization of water. The same is true for a weak base and its conjugate acid. So we can take a look at this example right here. All right, we have an acid reacting with water. The acid donates its proton to water. We have hydronium ions, and then we have our conjugate base. We can write the acid dissociation for this reaction. Similarly, here we have a base reacting with water. Water gives the base a proton. So now we have the conjugate acid and hydroxide ions, and we can write the base dissociation constant for this reaction. All right, now since the net reaction represents the autoionization of water, the equilibrium constant for the combined reaction is going to be the product of the individual equilibrium constants. The point here is if we add these two reversible reactions that we have written here, and note that they are just the reverse of each other, what we get is the autoionization of water. And that means if we multiply the value, the acid dissociation constant for the acid, and the base dissociation constant for the conjugate base, what we're going to get is our water dissociation constant, which is equal to 10 to the minus 4. So for any conjugate acid-base pair, this relationship holds true. And this relationship demonstrates that the strength of conjugate acids and bases are inversely related. If one is strong, the other is weak. So that means if you have a large Ka or Kb, you're going to have a small Kb or Ka respectively. Now, one important theme for acid strength is the effect of induction. Electronegative elements positioned near an acidic proton increase acid strength by pulling electron density out of the bond holding the acidic proton. This weakens proton bonding and facilitates dissociation. Thus, acids that have electronegative elements closer to acidic hydrogens are stronger than those who do not. Finally, the most common use of acid and base dissociation constants is to determine the concentration of one of the species in solution at equilibrium. This is very similar to what we have done with the equilibrium constants in previous chapters. So let me demonstrate this to you with an example problem. This problem says calculate the concentration of hydronium ions in a 2 molar aqueous solution of acetic acid, and the Ka value is going to be equal to 1.8 times 10 to the minus 5. Now, the first thing that we want to do is we want to write the equilibrium reaction. So this is going to be acetic acid plus water. It gives us our hydronium ions plus our conjugate base, which is just acetate. Now that we have this written, we can go ahead and write our expression for the acid dissociation reaction. Keep in mind that this is equal to the concentration of the products raised to their stoichiometric coefficients over the concentration of the reactants raised to their stoichiometric coefficients, and we do not include liquids or solids, so water will not be a part of this reaction. Our Ka is going to be the concentration of our hydronium ions multiplied by the concentration of our conjugate base all over the concentration of acetic acid. And this is going to be equal to 1.8 times 10 to the minus 5. We were given that value in the problem. Now, how are we going to go about solving the concentration of hydronium ions? The next best step is to set up an ICE table. We're going to set up our ICE table for our species of hydronium ions, our conjugate base, and of course, our acid, acetic acid. Now, starting off initially, we only have acetic acid, and we're told that we have a 2 molar aqueous solution of acetic acid. So the initial concentration for acetic acid is going to be 2 molar, but for our ions, it's just going to be equal to 0. Then we have to figure out our change in concentration. We're going to denote change as our variable x, and what we notice is that all of these species have a 1-to-1 ratio. So we're going to write that our change in concentration of our ions is going to be plus x because we're going to be forming our hydronium ions and our conjugate base acetate, and we're going to be using up our acetic acid, so this is going to be minus x. Now with that, we can go ahead and write our equilibrium concentrations. It's going to be x for hydronium ions, x for acetate, and 2 minus x for acetic acid. That means that we can now rewrite Ka. Ka is going to be equal to x multiplied by x over 2 minus x, and this is going to be equal to 1.8 times 10 to the minus 5. Now, this is a good place to remind you that you don't use calculators in the MCAT. So that means you can usually apply your 5% approximation rule and say that this minus x is negligible. And if you do that, then you can rewrite your reaction as x multiplied by x over 2. This makes the math a lot easier. If you were to keep your 2 minus x, you would have to use the quadratic formula to solve this problem, and you would definitely need a calculator for that. So by applying our 5% approximation rule, we omit the minus x. Now what we can do is multiply both sides by 2, and what we get is that x squared is equal to 3.6 times 10 to the minus 5. Now, something I'm going to do here is I'm going to move this decimal place 1 place to the right. If I do that, then I have 36 times 10 to the minus 6 now. And there's a reason I did this. The reason I did this is now when we take the square root of both sides, it's going to be a lot easier to work with because 36 is a perfect square. So the square root of 36 is going to be equal to 6. And then the square root of 10 to the minus 6 is just going to be 10 to the minus 6 divided by 2. So that's going to equal 10 to the minus 3. X is equal to 6 times 10 to the minus 3. Since our hydronium ion concentration is expressed as X, we know that our hydronium ion concentration is going to be equal to 6 times 10 to the minus 3 molar, and that is our final answer. Awesome. Let's move on to our last topic for this objective. This is going to be on salt formation. Salt formation is an important concept in acid-base chemistry, particularly in understanding neutralization reactions and then the resulting properties of those products. Now, a neutralization reaction is a chemical reaction in which an acid and a base react together to form a salt, and in most cases, water. Now, there are 4 possible combinations of acids and bases in neutralization reactions, and each one has a different outcome. We're going to elaborate on each one, but just quickly, the solubility rules that we've covered in previous chapters are going to be really important here. So as a friendly reminder, I've included them on this page of the notes so that you can refer back to them whenever you need. Now, what are those 4 possible combinations? Well, we can have strong acid, strong base, strong acid, weak base, weak acid, strong base, and weak acid, weak base. Let's go ahead and get started with strong acid, strong base. In a reaction between a strong acid and a strong base, the strong electrolytes completely dissociate into their ions. And the net equation reaction, which shows the essential chemical reaction, is just going to be the formation of water from hydrogen ions and from hydroxide ions. This results in a neutral solution with a pH of 7 because the acid and the base completely neutralize each other. Now we can prove this by taking this reaction as an example. We have hydrochloric acid reacting with sodium hydroxide to give us sodium chloride, this is our salt, and water. Now, looking at this is our molecular formula equation. We have all of the compounds in their undissociated form. The next step is to write the total ionic equation. Here, both the strong acid and the strong base will completely dissociate in water. So we can go ahead and write them in their dissociated forms like we see here. Now, sodium chloride, this is also a soluble salt, so we can go ahead and write that in its dissociated form as well. And this is what we get as our total ionic equation. Now here what we notice is that sodium cations and chloride anions appear on both the reactant side and the product side. That makes them spectator ions. And we can go ahead and eliminate them from both sides. And when we do that, what we are left with is our net ionic equation. And we notice that our net ionic equation is the reaction of hydrogen ions with hydroxide ions to form water. So the resulting solution is neutral. It has a pH equal to 7 because the hydrogen and the hydroxide ions completely neutralize each other to form water. Okay, what about strong acid, weak base reactions? So in a reaction between a strong acid and a weak base, the strong acid completely dissociates while the weak base reacts partially with the hydrogen ions to form a salt. The net ionic equation, it's going to capture the essence of this reaction, and it's going to highlight the formation of the conjugate acid of the weak base. And so the resulting solution is actually generally slightly acidic due to the hydrolysis of the conjugate acid. So we can prove this by looking at the following reaction. We have hydrochloric acid, this is our strong acid, and ammonia, which is our weak base, and they react together to give us ammonium chloride. All right, so this is our reaction. Let's go ahead, looking at this, let's go ahead and write our total ionic equation. In this reaction, hydrochloric acid and our salt, ammonium chloride, are both going to dissociate in solution. They're both soluble. So we can go ahead and write them in their dissociated form in the total ionic equation. And so this is what we get as a result. Now, when we look at this, we notice that chloride anions appear in both the reactant and the product side. So those are our spectator ions. We can go ahead and eliminate these. And what we're left with is our net ionic equation. Our net ionic equation demonstrates the reaction between hydrogen ions and ammonia to form ammonia. And so this resulting solution is slightly acidic because the ammonium ion can undergo hydrolysis, reacting with water to produce hydronium ions. Wonderful. What about weak acid, strong base? So in a reaction between a weak acid and a strong base, the strong base completely dissociates while the weak acid reacts partially with the hydroxide ions to form a salt and water. Now, the net ionic equation is going to capture the essence of that reaction, essentially highlighting the formation of the conjugate base of the weak acid and water. So the resulting solution is going to be generally slightly basic due to the hydrolysis of the conjugate base. And we can prove this by looking at the following equation here. So here we have our weak acid, our strong base, sodium hydroxide. They react to give us our salt and water. Now, our strong base and our salt are going to dissociate in solution. So when we are writing our total ionic equation, we're going to write them in their dissociated form. And what we notice is that sodium appears on both the reactant and the product side. So that is our spectator ion. We can go ahead and eliminate it. And what we're left off with is our net ionic equation. Now, in this net ionic equation, this is going to be slightly basic because the hypochlorite ion can undergo hydrolysis, reacting with water to produce hydroxide ions. Now, for our last scenario, weak acid, weak base, in a reaction between a weak acid and a weak base, both reactants partially dissociate and react to form a salt. The net ionic equation captures the essential reaction, highlighting the formation of the conjugate acid and base. And the pH of the resulting solution really depends on the relative strengths and extent of the hydrolysis of the conjugate acid and base. And with that, we've completed Objective 2, and we can move on to Objective 3. Well, I'm going to end the video here. In the next lecture, we're going to finish up the rest of this chapter. I hope this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.